I a hero?
Am I a hero?
Am I a hero?
Am I a hero?
We're here to challenge your definition of a hero.
All right, everyone. Welcome to the 10,000 Heroes podcast. My name is Nathan, and here's Ankur Shah Delight with me. Hey, Ankur.
Hey, Nathan.
How's it going, man?
Oh, fantastic. I'm still riding high from that interview.
Me too. And I just listened to it, and I wanted to say, I thought there was so much in this that really resonated with me, and that I thought hit the nail on the head in terms of what we're trying to do with this podcast. And I'll see if I can say it pretty quickly, because I think it might be helpful to point this out. One thing that my big takeaway was sort of liberating this process of inquiry, of scientific inquiry, which in his case, he's doing at maybe the highest level on Earth as a theoretical physicist, as a cosmologist, and liberating it from the hands of the experts and telling people that, hey, just by asking these questions, just by wondering, just by having this curiosity, you're right there at the cutting edge with the leading scientists in the world thinking about these things. And to me, that's this podcast in a nutshell. That this level of inquiry, this meaning, this connection to purpose is available to anyone, to everyone. In a sense, it's sort of like our birthright.
Yeah, it's what we're here to do.
Yeah, I mean, it's a proposition. I think it's an opinion we share, but regardless, how inspiring, just his passion. Here's what I thought. I thought, look, this relates. Here's the other point I wanted to make. This relates to one of our favorite quotes. I think we have this quote in common. This Victor Wooten thing, or that Victor Wooten TED Talk that we enjoy so much, and maybe we can throw a link to that in the show notes if we haven't done that before.
For sure.
But
worth doing every time, really.
Worth doing, maybe just at the top of the homepage. But yeah, Victor says in that,
renaming the podcast with just the link. The name of the podcast could just be the link to the Victor Wooten TED Talk.
I think that would serve our purpose just as well as people listening to us talk. But Victor says in that little talk, he says, if someone's putting you on a pedestal, don't come off of it. Stay up there and bring them up with you, right?
Yeah.
And so I love Neil deGrasse Tyson. Who doesn't? He's wonderful. He's doing the work, bringing science to the masses. But there's something in Neil deGrasse that to me feels like he is kind of dumbing down the process of inquiry to make it palatable. And I feel like Ethan isn't even glancing in that direction. He's just full on exploring what he's curious about, and in the spirit of generosity, kind of just making that available to everyone. That left an impression on me. Like, there wasn't a sense of, I'm going to give you the layman's version of this. This is like really pretty complicated stuff that I had to stop and rewind a few sections of this interview. And to me, that was really refreshing. It showed just an immense amount of respect. Maybe even respect isn't the word, but this mission to pay this kindness that he was talking about, this service that this professor did to him, to pay it forward and to pay it into the people that might be listening to his message.
Yeah. No, I love that. I love hearing your reflection on it. And for me too, it was, you started out the podcast going deep into, cosmology and theoretical physics and trying to understand what happened so long ago by looking so far away, and all these theories, the limits to what we know. But in the end, just ending up really at kindness and gratitude. Like that's what he got from all of those studies, for me, was kindness and gratitude. I was like, wow. Yeah. And I never would have imagined that was the conclusion.
Absolutely. There's so much more. I could just keep going on, but I think it'd be wonderful to just start and let people listen.
Let's do it,
because you did such a wonderful job. One thing I just want to blow you up a little bit. One thing I'm really appreciating these interviews, similar to the moment in Ken's interview, where you just say, "Hey, what's the deal with peace in the Middle East?" And like, these moments where we're talking to these individuals and you just go for it. So what's the meaning of life, man?
Hmm.
Where did the universe begin? And you certainly jump right into it. So let's get in. Everyone, please enjoy this interview with Ethan and Encore. Enjoy.
First of all, thank you, Ethan, for being on the show today. I'm really excited to have you on here. And I just know you primarily through this newsletter that you put out called Starts with a Bang. So I would describe you as a cosmologist. Is that how you see yourself?
I mean, that is my professional training, right? So a cosmologist is someone who studies a particular branch of physics and astronomy, like right on that edge of physics and astrophysics, where we're interested basically in this story of how the universe came to be, grew up to be the way it is today, and what its fate will be in the far future. So when we look out at the universe, we want to ask these questions of what is the universe? How did it become the way it is today? And what is it like on the largest scales? What is it like when you consider the whole cosmos? Where did it come from? How will it end? Did it have a beginning? Will it have an end? So these are the questions that I was really interested in when I applied to go to graduate school. And I was very pleased to learn, hey, you can specialize in this. This is a legitimate area of research that you could approach theoretically or observationally. I went the theory route. And then I got my PhD. I did a little bit of research afterwards. I became a professor. And it was while I was on that path that I really got passionate about science communication and communicating all that we know to not just other cosmologists or other physicists or other astronomers, but the general public. And that's where Starts with a Bang came from. I started writing it in 2008 when I was a postdoctoral researcher. And since I'll say about 2015, that was the last time I taught full-time at a college. Since then, I've been doing science communication full-time. So I'm a cosmologist turned science communicator.
Fantastic. And I want to get into some of these deeper levels of questions as to why it's important for, I'll say, lay people, not professional physicists, to understand this and its role in your life. But maybe before I do, could you just give us, if there is a simple and perhaps, is there agreement on how the universe came into being? Among the scientific community?
That's a good question, right? When you say, is there agreement? The answer is yes to a point, right? Mm-hmm. So if we say, okay, I'm going to step back through time and ask, how far can I go where everyone agrees? And,
right.
If you say, okay, I'm going to go back as far as the Hubble Space Telescope can see, everyone agrees that, yeah, like you see galaxies and structure in the universe, clusters, filaments, all of this growing over time. Here in the modern universe, things look a certain way because they've had 13.8 billion years since the Big Bang to gravitate, to evolve, to have all of these different dynamics occur. Stars have evolved, gas has evolved, galaxies have merged, etc. As you look farther back, because the speed of light is finite, so the farther away you're looking, you're only seeing objects as they were when light was emitted. So you're saying, oh, look, when I look really far away, I'm also looking back in time. So the farther back in time we look, what do we see? And the answer is, well, galaxies are younger. They're less evolved. They have bluer stars in them. They're smaller in mass. They have higher star formation rates. So we see all these signs that galaxies and the structure of the universe evolves over time. Everyone agrees with that. So you say, okay, well, can I go back to an area or to a time where there aren't enough stars so that the universe is transparent to visible light? Is there a point where all of these neutral atoms will actually block the light from stars? And yeah, we see that too. So then you go back farther.
I gotta stop you there. I didn't quite get that. There was a point where the density of stars made it such that light could not pass through.
No, this is great. So what you say is, okay, look, here in the late universe, right? What exists?
I just love that term, by the way.
Right. That now we live in late times,
okay,
right?
We're in the late universe.
This is how we think of it in cosmology. basically, if something happened within the first 3 minutes of the Big Bang, or at definitely the first fraction of a second, we call that the early universe or the very early universe. Something that happened, I'll say, before you form the first stars, because it takes time for the universe to cool and for things to gravitate and for radiation pressure to not push back against gravity. So you have all of this time that has to pass. It takes 50 to 100 million years for the very first stars in the universe to form. I would say anything between the first 3 minutes and the first 100 million years, that's what we call the late early universe. And then anything that happened over the last 99% of the universe's history, that's the late universe. That's the late time universe. That might not be everyone's definition, but that's how I conceive of it. So when I say today, yeah, the universe is late times. So what's happened? We formed a lot of stars. Stars emit ultraviolet radiation when you first form them. Like stars like our sun still emit a little bit of ultraviolet. But when you form stars, they come in all different masses. They have the little ones, the mid-sized ones, and the really big ones. And the really massive stars shine hotter and brighter. And that means they emit lots of ultraviolet light, which is excellent at ionizing atoms in the universe. So an atom, right, is nucleus with electrons. High enough energy light is going to kick those electrons off. So your neutral atoms become ionized. Now, here's a wonderful thing. If you take a look at the Milky Way at night, you don't see hundreds of billions of stars with your naked eye. You can only see a few thousand stars. In fact, even if you go to space and you take these powerful, powerful telescopes, you still can't see all the stars because there's all this neutral gas and dust in the way. In the plane of the galaxy, if you've ever seen the Milky Way, it isn't just shining this bright, luminous stuff at you. You have these dark dust lanes. You have these obscured regions. Those are neutral atoms. Neutral atoms block the starlight from behind it. So these neutral atoms, from very early on, they don't just exist in galaxies, but they exist in the space between galaxies, what we call the intergalactic medium. And if you have starlight that's coming at you and there's lots of neutral atoms in the way, they're going to block all of that visible light. In order to be able to see out past a certain point, you have to re-ionize those atoms. You have to have some ultraviolet light come in, kick those electrons off of those atoms so that the light can pass through without, getting obscured, getting absorbed by these neutral atoms. That's something this is very interesting to me, at any rate. When we look out into the distant universe, we can look back about, I'll say, 95% of the universe's age. We can look back about 13.1 billion years. And up until that point, the farther out we go, we see, oh yeah, everything is transparent to light. We can see everything. But as you start to go farther than that, you start to notice like, oh, everything beyond that is partially or even almost wholly obscured by neutral atoms. So we know there had to be a time where everything was neutral, and only once you formed enough bright, hot, blue, ultraviolet stars can the universe become ionized enough that that light can pass through unimpeded. And I think that's a really remarkable thing that we can look back and see, ooh, the universe has evolved in this way. If you want to look up the specific details, this shows up in quasar absorption features, and it's a feature called the Gunn-Peterson trough. So there's your $6 word.
Okay, fantastic. And that would also imply, if I understood correctly, that the very early universe would be difficult to observe.
That's right. We have to look for certain indirect signals of that. So one of the earliest signals we have is we can say, okay, look, if the universe was really hot and really dense and expanding and cooling, then you can imagine there was a time when everything was so hot that you couldn't form these neutral atoms at all, that anytime you had an electron bind to a nucleus, what happens? Well, one of these high energy photons comes along, it hits the electron, and poof, it kicks it back off. So you can't make neutral atoms. This only will occur, you'll only successfully make neutral atoms when the universe has expanded enough and cooled enough that there aren't enough of these high energy photons left to kick these electrons off. Well, what's interesting is when that transition finally happens, when the universe is a little less than 400,000 years old, so late early universe, what happens is the wavelength of this light has gotten stretched enough by the expansion of the universe that now it's not energetic enough to kick these electrons off of these nuclei. So when that happens, you form neutral atoms, and this lower energy radiation now is not visible light, it's mostly infrared light now. Most of this light can pass through the tiny, tiny neutral atoms because their wavelengths are longer. Mm-hmm. This is why we have infrared space telescopes, because they can see through that dust in the galaxy because it's looking at longer wavelengths. So that infrared light should come to us from when the universe was only a few 100,000 years old. And moreover, because the universe keeps expanding, it's expanded by about a factor of 1,000 in every direction from the time it was about 300,000-400,000 years old. Because it's expanded this much, now that infrared light has shifted to be 1,000 times longer in wavelength. Now it's microwave light. And that's where the cosmic microwave background, which is the leftover glow from the Big Bang, comes from. So that's a very early signal. We can go even earlier indirectly and say, you know, just like it was too hot to form neutral atoms, if we go way back into those first 3 minutes, it was too hot to form atomic nuclei. You'd get a proton and a neutron and they'd come together and something else would come along and smash them apart. So you can say, oh, well, I know my nuclear physics and I'm going to evolve this and calculate how much hydrogen, deuterium, lithium, helium-3, helium-4 should I form in the Big Bang? And you run your equations and you do your math and you get a prediction. And then you go out and you look at these gas clouds where there's either been very little or even no star formation and say, okay, how much hydrogen, how much deuterium, how much helium-3, how much helium-4, how much lithium-7? And you make those measurements, and that helps you test the physics of the early universe. So that's Big Bang nucleosynthesis. And that right now, I would say, is the earliest observable signature we have that confirms the Big Bang. We have other circumstantial things that we can say, for example, oh, we have some evidence that cosmic inflation occurred before and to set up the Big Bang. Unlike the Big Bang, though, which I would say like 99.9% of cosmologists working today accept it, I'd say probably only 90-something%, like in the low 90s maybe, are certain that something like cosmic inflation occurred. I think there were some holdouts there where people are like, well, but what about this wiggle room? And I don't think it looks good for people who are, you know, not in the inflation camp, but that I think is something where people are a little more tentative about what they'll say. And then as far as where inflation comes from, I wouldn't even go as far as to say we have a 50% consensus on that. I think there are many opinions and just not enough evidence to draw any conclusions about that. So if you want to go back as far as we can go, I would say Big Bang and everything in the aftermath of the Big Bang, definitely. Cosmic inflation, the case is really strong. It's much stronger than it was 20 or 30 years ago. But there are still a few, questions or detractors that have legitimate arguments. And then what caused inflation? What preceded inflation? I can throw a lot of complex words at you, but we don't have the evidence to know. That evidence does not exist observably within our universe. And that's what you always have to remember, I think, is everything comes back to Okay, but what evidence did you have for it? What did you observe, or what do you measure to tell scenario A from scenario
Sure.
B? And if you can't decisively tell them apart, which I say you can for the Big Bang and inflation in particular, I can think of 4 tests that were predicted before they were measured, and all 4 of those have come down in favor of inflation and not in favor of the Big Bang without inflation. So I think inflation's doing very well, and that if you want to do something other than inflation, you have a lot of explaining to do, but it's not necessarily a slam dunk. I give, I'll give the wiggle room to the people who like to wiggle. But before inflation, I think we have to be honest about what we don't know. And until we find some way of observing a signal that we haven't yet observed, or what sort of imprint might exist on our universe from a pre-inflationary time, it's very difficult to sort of say, this is the way things are going to be. This is what happened first. We don't have something like that.
Right. And so then what is your take kind of as a scientist for, when I learned about the Big Bang in high school, which is kind of the last time I seriously studied physics, there was no good answer to kind of what were the initial conditions, or what happened before that, or what's the, it very quickly devolved into a sort of kind of mystical shrug. Is that still how we are before that? What's the right thing to do as a scientist for, a kid asks you like, well, what about before the Big Bang?
That's a great question, though. Like, before the Big Bang is a great question. That's honestly how we came up with the idea for cosmic inflation, because without it, right, if you just say, okay, the universe is expanding and cooling today, that means if I go back in the past, things were smaller and denser and hotter.
Yeah.
And therefore, I can just go back as far as I want until I reach infinite densities and infinite temperatures, and everything in the universe is compressed down to a point. And then I have to ask, hey, how did the universe get to be this way?
Right.
If everything started from a singularity.
Well, if
and
all matter were in one point, that's the idea.
That's right.
Yeah.
And so there are really 2 approaches we can take. One is sort of the answer you got, which is to say, well, look, singularity is where time and space break down. So if we got to a singularity, we just don't know anything. How did it come into existence? Like, how do you talk about before there was time? Or how do you talk about outside of space? Right? That these are not really concepts we have. Like, space is all the stuff, so you can't be outside of it.
Yeah.
And
we're not equipped to really investigate that with our
feeble brains, right?
Yeah.
So that's the approach that I call giving up, right? Which is to just say, look, this is a question. This is for philosophers. This is for poets. This is for theologians. This is not for physicists, because we can't say anything sensible. Obviously, I don't like that approach. The approach I prefer is to say, okay, if the universe began with a singularity and it's going to have the properties that we observe today, then what types of initial conditions must it have been born with? If you want something, because birth of space and time, it could have turned out a lot of different ways. But we know in order to give rise to the universe that we see it, we have to have things have started a certain way. For example, when I look to the edge of the universe, the edge of the observable universe, 46 billion light years away in this direction, in one direction towards my left, and then I look 46 billion light years away in the opposite direction to the right, I could say, oh, well, there hasn't been enough time since the Big Bang for these 2 regions to have exchanged information with each other. There's no way they could have transmitted, light from one to another and light back to the other. The universe is expanding. They're too far apart. That couldn't have happened. So why do they have exactly to 99.997% precision? Why do they have exactly the same temperatures? Why do they have exactly the same densities? That's something that really only happens if something is in what we call thermal equilibrium, where it's had time to exchange information. Sort of like if I have a heater on one side of my room, It's going to take a while for that whole room to reach the same temperature, because for a while it's all going to be hotter by the heater and colder farther away from the heater. I basically need enough time for the universe to mix. I need enough time for the room to mix. And I know that in the universe, if I look in that direction and then the opposite direction, there hasn't been enough time for those to mix. So that's an unsolved question in the context of the Big Bang. Why would all these different regions that haven't communicated with each other, why would they all have the same properties? Also, another one is, look, if I'm going up to these high, arbitrarily high energies, then there should be leftover high energy relics from the early universe, things that get created at these super high energies, that when the universe cools, these stable things are left over. Where are they? Why don't we see them? Why don't we have magnetic monopoles, which are predicted in most extensions of the standard model? Why don't we have these massive, heavy right-handed neutrinos? Why are all our neutrinos left-handed? Where did the right-handed ones go? Why? So you can start asking these questions. And in the Big Bang, without anything else, they don't have explanations. You just have to say the universe was born this way. Or you can take the other approach, which is the one I like, which is to ask, okay, what kind of dynamics, what kind of physical dynamics could have created a hot, dense, rapidly expanding state with these initial conditions? What could have happened before the hot, dense, expanding matter and radiation filled state to set up and give rise to the Big Bang with these specific conditions? And then if I can find a theoretical solution to that, then I can ask, okay, well, are there any novel predictions that this scenario makes that the hot Big Bang without it doesn't make? Is there anything that I can say, okay, this new scenario goes and predicts something that I can observe, either an imprint in the cosmic microwave background, or an imprint in the large scale structure of the universe, or an imprint in something I can go out and measure? Does inflation, which is that theory, make different predictions from the hot Big Bang? And this was something that took a number of years of theory development to occur. People started thinking about inflation-like ideas in the late 1970s. Alexei Starobinsky was in on it very early, for example, but the big thing that moved the needle forward was in December of 1979. He was a young postdoc at the time, Alan Guth. He was listening to one of Bob Dickey's lectures. Dickey was this towering figure at Princeton. And Dickey was talking about some of these puzzles with the Big Bang. Why was it born with these initial conditions? Why, if the universe were born 0.0000001% denser, it would have recollapsed already. If the universe was born 0.0000001% less dense, things would have expanded so rapidly that we'd never have stars or galaxies. Why was it born with this perfect balance? And Alan Guth had this realization. He said, hey, if instead of being filled with matter and radiation and all of this stuff from very early times, if instead you had this state where all of your energy, and you had a large amount of it, but all of this energy was bound up in the fabric of space itself, then what happens? Well, this region will inflate, which is to say it will expand relentlessly, fast, and without decreasing its rate. This is different from what happens when your universe is filled with matter or radiation, because when I say matter, I think particles. When I say radiation, it's still particles. It's waves too, but it's also particles. If I expand my universe, right, if the volume of my universe increases, then the density has to go down because they have the same number of particles. So the same number of particles in a bigger volume means lower density, and lower density means your expansion rate drops. But what happens if this energy is inherent to space, when it expands, now I have more space. So the energy density is a constant,
Right.
but the total energy goes up. And that means I get a different set of predictions. It means, for example, that some of these puzzles with the Big Bang are all of a sudden explained. Why would the universe have the same properties over here on the left as it does over there on the right? Oh, because everything was together and then it inflated. And now these regions that look like they're disconnected, well, they were actually connected at some point in the past. Why? Oh, go ahead. Go ahead.
But wouldn't that mean that space itself has energy and therefore mass?
Yes and no. Yes, it does mean that space has energy. No, it doesn't mean that space has mass. And the reason is just because you can write E equals mc squared, which is how you can convert energy to mass, that doesn't necessarily mean that everything with energy has a mass. For example, a photon, a quantum of light, has an energy, but it does not have a mass. All of its energy is in a different form. Instead of E equals mc squared, it's in the form of E equals pc. Energy is momentum times the speed of light. So that's the, I guess I would call it the energy of motion term, as opposed to the rest mass energy term. Well, there's a third type that we don't normally talk about, and that's energy inherent to the fabric of space, which even today is positive and not zero, and that is the dark energy that we see. That's the thing that's causing the expansion of the universe to speed up. So all inflation is saying is that maybe very early on in the universe, instead of this little amount of dark energy that we have today, maybe there was an enormous amount of dark energy. And maybe that caused, once it went on for long enough and then it came to an end, now we can use your E equals mc squared to say, well, how does inflation end? And say, well, you have all this energy in space, but it's going to transition. And that energy, almost all of it, except for what's left over in dark energy, is going to get dumped into matter, antimatter, and radiation. But now, because it was set up by inflation, you can ask all sorts of questions about, okay, well, what will the density and temperature fluctuations that arose from these quantum signatures, if we assume inflation is a quantum field, what would they look like? What sort of structure will that give rise to? What sort of galaxies and galaxy clustering will that look like? And you get all sorts of weird and interesting predictions. But that's what we want, right? You want something where you can say, ooh, I came up with this idea. It explained the things that we used to explain with the Big Bang. So that's good. It also explained these observations that the Big Bang, we were just like, well, I guess it was born that way. No, Lady Gaga, we don't want to say it was born that way. We want to say, how did it get to be born that way? So you say, okay, well, you did that, but now what new predictions can you make? And these new predictions that I'm talking to you about, they were mostly teased out during the 80s, but the observations didn't come in until the 90s and 2000s and 2010s. So it's very exciting to me that we were able to say, I'm going to make these new predictions with a theory, and they're going to differ from my old theory's predictions. And now, as we're launching these sensitive satellites and we're taking these large scale structure surveys, we're going to actually start to see, how are these predictions borne out? Are they consistent with inflation? Do they rule out a non-inflationary Big Bang? I think the weight of the evidence is very strong, but there are other people who say, like, yeah, well, you're 4 for 4 with inflation, but what about number 5 that we haven't measured to adequate precision, or number 6, or, and fine, like, let's do more. Let's go out and get them. But when we do get them, boy, I sure hope this is the evidence that pushes you over the edge, because we really only needed one. One would have been awesome to be like, oh, we got one. Inflation's right. The Big Bang's wrong. Boom. That's what we did with Einstein. Einstein got the orbit of Mercury where Newton didn't. And then they had that total solar eclipse and the light bent. And everyone was like, all right, well, I guess Einstein's right. Better learn general relativity. And we've been doing that ever since. Yeah, we have more tests today, but they've really just confirmed what we already know. And I sort of think, cosmic inflation really is, we have incredibly strong evidence for that. In fact, I'm working on a book that I think people will enjoy, because I think most people who have experience with physics have a similar experience to you, where they learned the Big Bang was a beginning and it was a singularity and it was a birth of space and time, and we don't know what came before, and it doesn't make sense to ask what came before. And if you read Stephen Hawking's book, he says we don't know, and these same things. And that's not quite true, because we have the last 40 years of physics. We have cosmic inflation and all of this evidence. And I think that's a story that most people would enjoy knowing for themselves.
I totally agree. And I'm going to change the topic a little bit, because otherwise I'm going to blow our entire time on asking basic physics questions. So
they're fun, though. I don't blame you. I hope your listeners enjoy it too.
No, I'm sure they will. But now I want to tie this to, our lives. And, for me, the whole point of this show is to offer something to our listeners that they could integrate into their daily lives and really change their experience of living in some positive way. So maybe as a segue to that, why is it important for people who are not cosmologists to learn about this stuff, or to know it, or to investigate, even just to investigate these questions?
I think that there are some very, very big existential questions that we all wonder about at some point or another. Questions like, where did we come from? How did we get to be here? Where are we going? And why is there something rather than nothing? Why do we exist at all? How did we come into existence? These are questions. These are big questions that I've wondered about since I can remember wondering at all. I can't compel you to be interested in that if you're not inherently interested in that, but I think so many of us have that desire to know, I guess, the answer to as many of the cosmic mysteries that we wonder about as we can. I remember being a kid. I grew up in a city, so I didn't have the experience of a dark night sky very often, but I remember camping as a kid, going up north into the mountains. And I remember being on a hillside one night when it was clear. And, I know where I was now. I couldn't see the Milky Way. I was probably able to see about a few hundred stars. And that felt like infinity to me. That felt like so many, that this big black sky with hundreds and hundreds of glittering stars was up there overhead. And I just sat on my back, laid in the grass. And after a while, it felt like I was going to fall up into the stars. And I remember digging my fingers into the grass to hold on, to make sure I didn't float away. And, this is when I was a kid. So this is way before any, ways I may have fried my brain later on. So this is, this is like, wow, like, I think most of your listeners can remember, if not that exact experience, can remember some sort of experience where they wondered about that. I remember wondering when I learned a little more about geometry, hey, I wonder if I traveled in a straight line in space for long enough, would I eventually come all the way back around and come back to my starting point, just like if I walked around the Earth for 40,000 kilometers, I'd return to my starting point there. It turns out these are not dumb questions. These are not dumb musings of someone who doesn't know any better. These are serious ideas that we can investigate. and that we can learn something about. And in fact, that's for me, one of the most exciting things about the science of cosmology is these are the very ideas that we started exploring and developing and sort of saying, oh, wow, we can actually learn whether our universe is rotating in some sense or whether it isn't rotating. We can learn how it's expanding and what's in it and how that expansion rate has changed over time. And we can learn about the earliest moments of the hot Big Bang. And if we understand inflation, we can even learn what came before and set up the hot Big Bang. And then going forward, we can learn what's going to happen in the future. We can learn what's going to be the maximum size of a structure that forms before dark energy pushes everything apart. We can learn how long will the stars live until the universe has no more stars in it. These are questions we can start answering. So I would say, if you are interested in learning where we all come from, what the cosmic story that unites us all is, what reality is to the best level that we know it, and where things came from and where things are headed, I think these are questions that people have wondered about for at least as long as recorded history exists. And so the fact that, I would say, mostly in the 20th and 21st centuries, we had these questions that had been with us always, that we finally started to be able to come up with scientific answers to them and learn, where did these things come from? How did the universe begin? What happened? How old is the universe? Like, it's crazy that the universe had a birthday. The universe had a day where it wasn't like the universe, where it wasn't full of matter and radiation and expanding. It wasn't doing that before a certain day 13.8 billion years ago. And then it was born as we know it, and now it's doing its thing. Maybe it won't keep doing it forever. Maybe we have something else coming down the line. I think if any of these questions are something that you wonder about, that the first thing I'd want to do if I were the one wondering about these questions is I would want to go out before I began speculating. I'd want to go out and say, well, what do we actually know? What do we have scientific knowledge about that can bring me up to the frontier? And then I can speculate as to what might be beyond the frontier. I can speculate, I can listen to other people and what their ideas were and why they have those ideas about what lies beyond that frontier. But it's sort of like, if you want to peer over the horizon, your best bet is to first open your eyes and look out at the land that's before the horizon. And that's why I think learning about cosmology, learning about this science is of such interest to people, because if you want to ask these big questions, you should at least learn what we know so that you can approach those questions without being 40 or 100 years out of date in the science you approach it with. I sort of look at these old philosophical attempts to prove the existence of God based on cosmological arguments. Well, if you don't understand cosmology, then you're going to be arguing from some incorrect assumptions. No, start with the correct assumptions. We know them. I want to teach them to you. Like, you can do this. This is something that can be known by humans and can be known by non-experts if it's presented correctly.
Beautiful. And now I want to take that kind of universal and cosmological and bring it back to the personal. In what way has this journey brought you a sense of meaning? I mean, you clearly have a sense of purpose and passion and dedication. How has this figured in that journey for you?
That's an excellent question. I think maybe one of the biggest influences on me was my advisor. my PhD supervisor. His name is Jim Fry, professor at University of Florida, a theoretical cosmologist. And I remember how excited he was to always tell me, to share with me what he knew to the limits of how he knew it, that it didn't matter to him if I was asking him to go through the details of something for the third or fourth or fifth time. He was always happy to do it. And for me, having someone who was that invested in me learning not only the things he knew, but the things I was curious about, it was sort of transformative to me in the sense that, yeah, I had always been interested in teaching and education and, informing people as to what they know. But the way he did that with me really made me appreciate, he poured this time into me. He poured this care. He poured this effort into me because I wanted to know, and he thought it would be valuable if I knew it. The best thing you can do is to extend the same kindness that someone else showed you to others. And so for me, doing this education work, doing this labor of taking these complex topics and breaking them down so non-experts can understand them just as well as experts, that is that same spirit of kindness that was shown to me. So in my own way, I feel like I'm passing that on. I'm passing this knowledge, this passion, this curiosity. If you have it, let's open these doors up to you as well. And for
I
me,
love
I
that.
think that's the human connection, is someone showed me a kindness in a way that empowered me to show that same or similar kindness to others, maybe even on a larger scale. And so for me, that was a way that I would say a good behavior was positively modeled for me. And that in a way sort of became my default attitude. And I think that's, a lot of people are like, well, why would you do that? Why would you think to do that? And it wouldn't have occurred to me to think differently because this was my experience. I had the good thing as my experience. And I thought, well, if I had this good thing and it was a good experience for me, let me do my best to make others who are curious about this have that good experience too.
Yeah, that's so beautiful. And I love how you break down all of like our academic and educational traditions into the passing on of kindness. That's such a great way to reframe it for me. So then let me ask you, you've written a couple books, you've got this podcast, you have this Starts with a Bang newsletter. That's how I met you. What is this vision of passing on this kindness? What does that look like in 10 years?
In 10 years, wow. So this is a good question, because if you had asked me 10 years ago, where would I be in 10 years, or 10 years before that, when I was a beginning graduate student, where I'd be, I would have guessed wrong, because the thing I'm doing now didn't exist back then. I had to create it. So when you start asking me, what would you like to be doing in 10 years? I sort of think about, what would I like to create? And I think the biggest things I would like to create are high quality video, maybe television, maybe film productions that bring these cutting edge frontier science stories to as wide an audience as possible. I think that people have that curiosity there. And if I can be the one who brings it to them to the best of my ability, then that's a worthwhile use of my time and my energy, is to sort of say, you know what, let's get the best information that humanity has to offer to as wide of an audience as possible, without sacrificing depth or accuracy. Let's make it so that if you listen to this, if you watch this and you absorb what's in there, that you are right there on the frontier with all the cutting edge scientists looking out at the landscape of what's known, what's possible, what our next steps are. And let's bring you that same sense of wonder and awe.
I love it. And then what is your metric or your indicator that you'll have had the impact that you're looking for? Like, will
You
I know by
know,
the number of people applying to cosmology grad programs, or the number of people that feel meaning in their life or connected to all the other sentient beings in the universe? Or what's the
I
indicator?
mean, there are lots of different ways to define success. I remember thinking a few years ago when I was able to leave my day job and, devote myself to science communication full time. I remember that feeling like an enormous milestone that, wow, I've actually made a job and a career for myself doing what I've wanted to do, and I'm not dependent on anyone else for it. So that was a big milestone for me. But it's kind of funny now. You are reminding me of a time when I was in I think it was seventh grade. Um, we had this class called Home and Careers. It was the equivalent of home economics in a school where we didn't have a gas stove or oven, or we couldn't cook basically. Like, look, we were a public school in Yonkers, New York, and they didn't trust us with anything sharper than butter. So it's fine. But we had this class and we had this wonderful teacher, Mrs. Brown. And one of the things Mrs. Brown taught us was she went and asked us all what our dreams were. And, we're kids. So most of our dreams are like, I want to be a pop star. I want to be an astronaut. I want to be a sports, star. These are our dreams. And she's like, okay, how are you going to make those dreams come true? And we were like, well, what? Like, well, to just be the best at what I do. She's like, no. You want to turn your dreams into goals. And for you to turn your dream into a goal, you need to think about what are the steps you're going to take so that you can be successful however you define it. So I think for me, it's to sort of think about, what do I want to be doing? And then if I can do that and I can make this happen, that is success. Success is doing the best job you can do at the thing you're trying to do. That doesn't mean, oh, I'll know success because someone will give me a Nobel Prize, or I'll know success because someone will give me $1 million, or I'll know it's success because all these people will be talking about me and I'll have my 15 minutes of fame the way that people dream about. Those aren't going to do it for me. The thing that's going to make me feel successful is if I get that internal sense of satisfaction that I took on a challenge, I did it to the best of my ability, and I'm pleased with what came out of it. I'm pleased with what resulted. That's success to me. That's meaning to me, because for me, that big question that people ask about what's your meaning to life, it was very freeing for a lot of people. They view it as like someone's watching them and judging them. Like, oh, if you don't live your life the way you're supposed to, you're doing it wrong. And then you're going to be judged and things are going to happen. Like, it's very freeing for me to say, the only meaning that we have in this life is the meaning we ourselves put into it. So if kindness is important to me, then I want to be kind. If educating people is important to me, then I want to give them the opportunity to get that education. If it's important to me to tell these stories in a compelling way, then I want to tell those stories to the best of my abilities. And I might get some external feedback that's meaningful to me, but none of it's really going to compare to the internal feedback you get of, am I satisfied with the job I did? Am I proud of myself for what I've accomplished? And so I don't look at it as some like, oh, it's some long road. And when I get to the end, 30, 40, 50 years from now, if I look back and I'm like, did I do a good job? And if I can say yes, or if someone else can tell me yes, I'll be satisfied. It's more like, when I put my time and effort and energy into something, and I do that work and I accomplish something, or I create something, am I proud of myself for what I've done and how I've done it? And for me, those questions are just as dependent on the answers to questions like, who did I help along their journey while I was taking my journey? Who did I uplift with me? Who did I accidentally leave behind? And what can I do to make sure that they aren't left behind anymore? It's really this, it's really about how you take your steps along your journey. Just like when I was an active research scientist, I realized it's not all about that end goal of I'm going to tackle this problem and I want to solve this problem, and if I can do it, I'll be satisfied. It's also about that day to day. Hey, every day I'm going in and I'm making incremental progress on this. Am I enjoying the work I'm doing each and every day, the day in, the day out? Is it a slog to me, or am I excited and happy to go in every day and work on this? I think when we think about satisfaction in our lives, we all too often get caught in this trap of looking at our big accomplishments and saying, did I do enough? Did I do what I should have? Instead of looking at, here's what I'm working on, here's what I'm walking towards, and here's the step I took today, and here's the step I took over the past week or month or year. It's not all about what you achieve. It's also about how you go about your life every day, who you're kind to, who you're good to, who you positively impact. And a lot of times you'll never know.
Yeah, that echoes really strongly with me too. And it reminds me of something else that you may think about a lot as a cosmologist. Cosmology, the study of the beginning of existence. I'm sure the whole specter of non-existence plays a large part in that. How do your thoughts about mortality or relationship to death kind of influence your decision making?
That's an interesting question for me. I remember there was none of it that I really knew in my life until I was a child, and I was maybe 7 years old. And when I was 7, I had a bunch of things happen all at once. One was my uncle. I think this happened the year I turned 6. My uncle, my dad's little brother, was in a car accident where he lost control of his car. It went into a lake and he drowned. And they tried to revive him, and he was on life support for months. And I remember visiting him in the hospital.
Wow.
But he never woke up. He never regained consciousness, and he died. And then within a year, his mother, my grandmother, she died as well. She got ovarian cancer, and, looking back on it, likely lost the will to live, and she died. And over that same time, two other people that I knew, one was this woman named, I think, Ronnie. She was friends with my mom, but she had cancer and died. She also had a kid my age. And so, I was friends with her until she died. And then that was that. And one of my other best friends, Peter, his dad was very sick. And I think when we were 6, his dad died. And so all of a sudden, for someone who had no experience with death, like all of these people that I knew and were close to and loved, they were gone.
Yeah.
They were gone and they weren't existing anymore. And I remember feeling like this sense of loss because they were really gone. I remember being worried about dying and asking my grandmother before she died, if there was life after death, could she come and tell me? Could she come and tell me that she was okay? And for months and months and months, I waited for her to come to me in a dream and tell me, and she never did. And in the mind of a kid, like that's an influential thing, even though, as an adult, you question the kid's logic, but as a kid, that's one of those things where you're like, oh man, like it's just us for just this temporary amount of time, and then we're gone forever and ever.
Because if there were life after death, you would have known about it. She would have.
I mean, Grandma would have told me, right? She loved me. Why wouldn't she have just come to me? And now when I get visits from my dead friends or relatives in my dream, I think of it pretty differently. I think about it as like, like I have unfinished things that I'm processing in my head, not like, like, oh, this is a visit from beyond the grave that I'm getting. But but I'm not going to tell people what their dreams do or don't mean. I'll just tell you like what my experience was. What I started thinking about though was, if I'm curious about what the limits of existence are, then what it would do me a great service to learn. It would help me if I knew all that we knew about physical reality. So if I wanted to speculate about what was unknown, what was beyond what we knew, at least I was getting the what we knew part right.
So this series of events, when death kind of comes on the scene for you as a 6 or 7 year old, it's pretty linked to how you ended up living your life and what you chose to study.
Uh, you know, Perhaps. I mean, maybe you can say that. I'm someone who was very curious about a lot of things. So I wasn't really sure that being a cosmologist was what I wanted to do until I was about 22 years old. So I had already gone through my schooling, gone to college where I majored in 3 different things because I wasn't sure. And then after I left college, I went and became a teacher before I ever went to graduate school. But it was while I was doing that, while I was a teacher, that I decided, this is okay, but it's not what I want to be doing for long. So if I could take the next step for myself, what would that be? And that's when I sort of was like, well, I would want to know the answers to these big existential questions of what is existence? Where did the universe come from? How old is it? How did it get to be this way? And then it was like, oh, but that is a scientific field. It's a branch of astrophysics. Specifically, I'm interested in the theory of it. It's called cosmology, and I can study it. So I went and applied to graduate schools where there was someone who was a theoretical cosmologist that I could say like, well, maybe I could work with this person. And when I visited Florida and I met Jim, I was like, this is the guy. This is where I want to be. I would be okay living here. I think the overall department is very strong here. But most importantly, he's the person that I want to work with. And that was kind of unique, or that put me in sort of rare territory as a grad student. I would estimate that of the incoming grad students who came into that year with me, I would say only about 10% of them knew what they wanted to study and who they wanted to study with. So 90% of people are in there taking the core courses, trying to figure that out. I'm in there thinking like, that's who I want to work with. What can I do to impress him enough where he would say, I'm willing to take you on as a student?
Yeah.
Um,
You had the vision.
I had a vision at any rate. I won't say it was the vision because, like many things, I've taken twists and turns over my life where I've changed my direction somewhat numerous times. But I don't discourage anyone from doing that. Take the step down the path you want to step down. And if it's the wrong path, you can always take a step in a different direction. But if it's the right path, you'll be glad you stepped forward when you did.
Beautiful. And I have one more question, and I think something you and I share is a love of gratitude. And you've already kind of shouted out to two important teachers in your life. So I'm just wondering if there's anyone else you want to highlight their contribution or thank them, a parent or a student or a friend or someone that's really been influential in your life.
You know, there are a lot of people that I commonly thank. So let me take this opportunity to thank someone that I don't know if I've shouted out before. And that is my high school AP chemistry teacher, Mrs. Sporn. Mrs. Sporn was, she was the AP chemistry teacher in the school. And I often had this thing where if we got a problem, it wouldn't occur to me to solve it the way we're taught to solve it in the book. If there was a way that was like superior to me to solve it, or an alternative way that I thought was an interesting way to explore it. And so when she would call on me to go up to the board and solve a problem, I would do it. And if I got it right using a different method, it would take her a minute of surprise, but she never discouraged me from doing it that way. And in fact, at the end of the year, she got me a little present. It was a book. It was a book by Michio Kaku. It was called Hyperspace, and it was in many ways my first book about speculative theoretical physics. It was the first book I had that was like, okay, so like, we're going to go beyond what physics knows, and we're going to start putting these crazy ideas in here of extra dimensions, of string theory, of all of this stuff. Now, as an adult who is a physicist, I look back on that and I have mixed feelings about it, because some of the things in there I recognize are not true and some of them are not accurate. But also, that was a moment for me where someone else encouraged me not only to wonder about things that I hadn't wondered about before, but where someone I felt encouraged me and gave me a push to say, hey, you might be interested in this. And if you are, here is a start to exploring it. Now, I don't know that I learned all the right lessons, because when I went to college after taking Miss Sporn's class, I was convinced that I wanted to do chemistry, not physics, because she was such a good chemistry teacher. Like, her passion, her competence, her knowledge, the way she approached it, it resonated with me so strongly that I was like, maybe this is what I want to be doing. I mean, what are we doing in physics? We're sliding blocks down ramps. What are we doing in chemistry? We're learning about how electrons in atoms and molecules are shaped in their clouds and bind together and do, like, which one of these is more interesting? I'm going to go with the chemist. And I got him more into it. And I was like, okay, so I loved Mrs. Sporn, but I actually love physics and not chemistry. But she was someone who I think encouraged me to explore a particular direction at a time in my life where I wasn't getting a push in a clear direction otherwise. And I think that that was something that just meant a lot to me at that time in my life. And I think that a lot of people don't realize how a small act of taking an interest in someone else can actually help push them down a path that they'll be very glad they went down.
Yeah, yeah, that's beautiful. Do you have any kind of parting words or anything you'd like to suggest or recommend to our listeners before we adjourn for today, Ethan?
One of the things that I was expecting to be asked about is a little more about my idea of a hero, because heroes are honestly something that I've struggled with, because for me, they often come along with an urge to sort of deify the person you admire as a hero, because you don't want to say, like, well, I view this person as a hero, but they also have these flaws. They also did these things that maybe I wouldn't be proud to have done. They also, the person who spurs my interest on in theoretical physics may also be a person who has their own ideas that they mix in that might be very speculative with the actual known ideas. Well, take the aspects of the person that you find heroic, admire those, internalize those, try to make those best aspects you see them a part of your life, but don't be so slavish to the idea of a hero that you don't look at the flaws they have and make sure to not develop those same flaws in yourself, right? Have your heroes, but accept them as they are, and don't feel the need to make excuses for their flaws. Just do your best to be the best version of yourself that you can.
Beautiful. Okay, I got one last question. I can't resist. I thought about this even before we were talking. I was like, all right, you're professional. You look at stars all the time, either through photos or reconstructed simulations. Do you still have a sense of wonder when you lay down and actually look at the stars in the night sky?
I mean, there are a lot of people who think that when you understand something too well, it loses its beauty. And to anyone who thinks that way, I'd like you to consider this. When you look at someone you love and you look at them after knowing them for 10 years, for 20 years, for a really long time, whether it's a parent, a spouse, a partner, or a child, do you love them less because you're more familiar with them? Or when you look at them, do you see things in them that are wonderful that when you look at them, you're the only person who sees them with the viewpoint that you have? So when I look up at the night sky, it's not the same sense of wonder that I felt when I was a kid. But in many ways, I think it's a bigger sense of wonder. I think when I look at that, I don't just see what I can see with my eyes. I know how much more is out there. And I know that when I'm looking at that little smudge in the sky that corresponds to Messier 31, the Andromeda galaxy, I know I'm seeing an object that's 2.5 million light years away with my naked eye. There's so much that's out there beyond that, that I think my sense of wonder is larger than it's ever been. I'm no longer worried that I'm going to fall up off of Earth into space, but I don't see it as holding any less of an amount of wonder for me.
Thank you all for listening to today's show with Ethan Siegel, and check out the show notes for more information on his work. And as we mentioned at the beginning of the show, Victor Wooten's TED Talk, of course, always something to keep at the top of your mind. So thank you, and we'll listen to you next time, or you'll listen to us next time.
It's a conversation.